Okay, today's webinar is brought to you by EPA's Office of Underground Storage Tanks and Office of Research and Development. PVIScreen may be used to develop a modeling-based line of evidence to assess the potential for petroleum vapor intrusion, or PVI, impacts on buildings and help regulators make better informed decisions. PVIScreen is intended to be used in conjunction with OUST's technical guide for addressing petroleum vapor intrusion at leaking underground storage tank sites. And our presenter today from ORD is Dr. Jim Weaver. He is the developer of PVIScreen. Dr. Weaver has worked to support the Office of Underground Storage Tanks for over 25 years. His research focus is on the application and development of models and their supporting data for assessment of leaking underground storage tank sites. Now I'll turn control of the webinar over to Jim.
All right, thanks, Hal, and thanks everybody for joining today. I'm going to start out with an introduction and basis of PVIScreen, and so I have a PowerPoint that will take about 45 minutes to go through, and then after that I'm going to launch into a live demo where we'll go all the way from downloading the software to running some of the example problems, and we'll see, you'll see hands-on how it works. I'm really intending this to be more of a demonstration than a type workshop, but you're welcome to try to go along with it. For practical purposes, it's going to be mostly me showing some things, but I think you'll find seeing this worthwhile. And then we'll have some time at the end for questions. So let me get started. So I've titled this Assessing Variability in Petroleum Vapor Intrusion with PVIScreen, so that really my focus is on how do we assess this variability rather than focus on the model. But of course we will talk about the model as we go. Okay, so as an outline, I'm going to start off with some general insights on environmental models. I'll then talk about vapor intrusion in general and petroleum vapor intrusion. I'll talk about, as I said, the PVIScreen model. I'm going to give some excerpts from examples that we have in the user's guide, and I want to focus on two situations. One where the model is indicating the potential for PVI and one where it's not. So you can see the character of the output when you get either one of those situations. And then I have secrets of PVIScreen that won't be secret after we get to that slide, but there's some things about it that need to be kept in mind. And then I'll go through a summary and we'll talk about availability, which is just clicking on this link. And then, as I said, I will launch into the live demo. Okay. So why would we even consider models when we assess vapor intrusion? Well, of course, there's technical challenges that I'm sure everyone is aware of. Ambient air can have the same contaminants as those we might think were coming in from the ground, and so that's a challenge. There can be internal sources in sinks of the same kind of contaminants that we think may come in from the ground. You know, one of the simple examples is if you have an attached garage and you have gasoline for your lawnmower, you might end up having these petroleum hydrocarbons in the air in your home, but they didn't come from the ground, they came from the gasoline. So there's a lot of challenges in measuring indoor air contamination. There's social issues. RPs, responsible parties, or homeowners may be reluctant to sample, and we don't have an authority to force them if they don't want to. And then in some cases, this is the brownfield situation. If you're redeveloping a site and a building has not yet been built, that is kind of a classic case for where we would want to use a model to project the potential impacts for something that has yet to come to pass. Okay, so if we think back to the year 2000, there was a series of articles published in the Denver Post that discussed various aspects of vapors in buildings, and one of those articles talked about a model that was used, and it was called the Johnson-Ettinger model, and they found a presentation that someone from EPA had actually given that said that sometimes it overpredicted and sometimes it underpredicted indoor air concentrations. And this model was being used to screen sites. But the model was being used with mostly default parameters and only a very few site-specific parameters, and it wasn't being calibrated to any measurements. So it's really no surprise that this model alone wasn't very good at predicting, a flat-out prediction of indoor air concentrations. Okay, to hammer this home a little bit, if we all think back to our introductory geology or hydrogeology class where we learned about Darcy's Law. So Darcy's Law purports to tell us something about how water moves through a porous medium. So Darcy, in his experiments, discovered this relationship, which I've termed the Darcy flux, or sometimes it's called the Darcy flow, that is then related to the hydraulic conductivity times the head gradient. Okay, and so this is a relationship he determined from his sand tank experiments when, just to relay the history, he was designing filters for the city of Dijon, France in 1856. So he determined this relationship, but it has an empirical coefficient called the hydraulic conductivity. And you only know the hydraulic conductivity from making a measurement, measuring it. And so over on the right-hand side of the figure, I've put a table showing some generic material types and hydraulic conductivity values. Okay, and these differ greatly from each other. And you can't really say that you know much about how water is going to flow through this column unless you know the value of this coefficient. And then it's also interesting, most of the places, textbook type references, where you're going to look up these values, you know, for a generic classification, it gives a range of values. Okay, so there's uncertainty unless we're going out and measuring all these parameters. Okay, one of the people that has written a lot about uncertainties in environmental models is Professor Naomi Oreskes, who's now at Harvard, but she's written some of the best stuff, I think, on environmental models. And in one of her papers that I've listed here, she gave examples of ideal model applications for environmental situations. And the one that's maybe most enlightening is weather forecasting. So when I read this, I thought, why would this seems to be a bad example, because the forecasts are often or usually wrong. Well, it turns out it's a good example for the reason that the weather forecast is given as a probability or given with uncertainty. And as important as it is that it's given with it, it's that we receive it with that uncertainty and we accept that uncertainty. Okay, so I don't think anybody, or maybe I'm sure somebody has, but we don't call up the TV station and say, don't give the weather forecast because it was wrong today. We accept that it might be wrong, but it might be a useful guide to how we want to carry out our day. Okay, so now to get back to vapor intrusion. And this I'm putting in for background because I'm sure most people are aware of most of what I'm about to say. Chlorinated solvents on the left and petroleum on the right are basically distinguished by their prospects for biodegradation. So in the case of the chlorinated solvent, or dense non-aqueous phase liquid, DNAPL, when it's released, it flows down to the water table. Being more dense than water, it can finger its way through, maybe pond up at the bottom, cause contamination in the groundwater, and then these vapors coming off the DNAPL can pretty much perfused through the vadose zone. Contrast on the right, the petroleum hydrocarbon that's released from a tank flows downward. It gets to the water table. It's less dense than water, so for the most part we find it hanging around somewhere around the water table. It too can create contamination in the groundwater and vapors in the vadose, or the vadose zone. But it's distinguished by the fact, both in groundwater and in the soil gas, there's the potential for aerobic biodegradation. Okay, this is not the case with chlorinated solvents, where they pretty much do not degrade under aerobic conditions. You need strongly reducing conditions. But for petroleum hydrocarbons, there's a large capability to have biodegradation. And one of the reasons for this is just there's a tremendous supply of oxygen in the atmosphere that can diffuse into the vadose zone. And if we did the math, we have 21% oxygen in the atmosphere, and that's compared against concentrations that are on the milligram or microgram level per cubic meter in the ground. And so there's a vast supply of oxygen. And this, it turns out, is a major characteristic of petroleum vapor intrusion. Okay, but this is situational. It's situational because it depends on, well, where's the bottom of the building relative to the contamination? So if we were to move the water table up, or if it just wasn't as thick, maybe this contamination does get into the building. And then if the building was located over here near the source where there's this residual nap bowl, well, maybe that would be a situation where it could get in the building. And so those are two kind of visual factors that you can see on this schematic. But then there's others also, because it may depend on the moisture content, or it may depend on the porosity, things that we don't really see on this schematic. But there are a number of factors that are interacting here to determine if these vapors can actually get into this building. Okay, and just a little bit more on biodegradation. I mentioned the oxygen flux from the atmosphere. So oxygen is coming down. If this is the impacted soil, or it could be impacted groundwater, as these petroleum hydrocarbons and methane could be also, as they come up, they're encountering this flux of oxygen, and with the naturally occurring bacteria, there's a reaction zone. So oxygen is coming in, carbon dioxide, oxygen concentration is decreasing, carbon dioxide concentration increases, and the consequence are there's a zone of biodegradation, and the petroleum hydrocarbons decrease. All right, so that schematic, is a fine concept, but it's based on data from the field. And what I've showed here is a depiction of one of the data sets and one version of the data sets that have been used to demonstrate the commonality or the commonness of biodegradation of petroleum hydrocarbons. And the data are represented as the thickness of clean soil needed to attenuate the vapor. So it's something like this red arrow is what is plotted on this vertical axis, and then it's plotted versus concentration. So one thing you can see is if you look at concentrations below about 1,000 micrograms per liter, you'll see about 5 feet is about enough to degrade the hydrocarbons. And when you look at higher concentrations, from 1,000 micrograms per liter on up to tens of thousands, that are more characteristic of the presence of the separate phase gasoline, it's still not tremendously more. It may be on the order of 10 feet or so. Okay, so this is for benzene. There's similar data available for TPH. So you see the same sort of thing. These data points, each data point may represent a soil gas profile. It may represent more or less amount of data, but when you put it together and display it this way, what you see is there are these varying distances on the order of 5 feet if it's dissolved in groundwater only, or if there's free phase present, it could be on up to 15 feet. And the heading of that slide, of that previous slide, was the PVIScreen rests on a foundation of field data. So it's really this understanding that biodegradation is happening based on the field that allows us to have confidence that we can put together a model that includes biodegradation and that it ends up working to correctly represent these processes. Okay, so that kind of data are discussed in OUST's technical guide for addressing petroleum vapor intrusion at leaking underground storage tank sites. ORD worked with OUST in developing this over a several-year period. And one of the things in the document is a flow chart for evaluating and making decisions at sites. So I just want to talk about this flow chart for a minute. It's going to be hard to read. I don't read it very well on my screen here. But this is a flow chart for a site assessment. And what I did was I highlighted part of this flow chart in gray. And the red circle is where you have someone complaining of vapors in their house or something. And so this is where there's an immediate threat. Okay, we're not talking about PVIScreen for immediate threats. That has to be handled first. And after the immediate threats are handled, then we would go into assessing the site or characterizing the site and developing a conceptual site model. Okay, and so PVIScreen really isn't in those initial stages. It's definitely not in the immediate threat stage, but it's to be used in assessing the site once we are characterizing the site and once we are beginning to assess it. Okay, and on here are two red marks. And those are two possible places where the model could be used. And this first box that's indicated by the arrow right now is determining a vertical separation distance, because that's one of the things discussed in the guidance. So PVIScreen could be used in parallel with assessing the vertical separation distance. And so that would be one potential use. Now, if it turns out that your assessment of the vertical separation distance is really marginal, maybe you can't really tell if there's 5 or 10 feet of clean soil, and maybe it's not clear from the site data. That's another situation where you might want to apply a model or apply PVIScreen. Okay, this just highlights the distances again. This is copied out of the OUST technical guide, and it just illustrates this situation. So for groundwater, if there's no NAPL present and the concentration is less than 5 milligrams per liter in groundwater, less than 30 of TPH, separation distance of 6 feet is the screening criteria given in the guide. Well, like I said, maybe there's a marginal situation where you can't be sure, so you could use PVIScreen to develop a second line of evidence. Okay, so here's the user's guide. At this point, let me acknowledge my co-author, Robin Davis, who's now retired from the state of Utah. She helped in generating case studies and with putting together the field data that we represent in the user's guide. This is downloadable from the web link that's given here and is also in this side box. And we will go to that link later on when I start the live demo. Okay, so we talked about the background for PVI, talked about a background in models. What exactly is in PVIScreen? So it includes the model itself, which is based on biovapor, which was developed by George Duvall. So it's the same basic model equations as are in biovapor. They have been recoded in Java. biovapor runs in an Excel spreadsheet. Java, this is recoded in Java, so it runs faster. Java runs much faster than Excel. Then added to that is an automated Monte Carlo uncertainty analysis. Monte Carlo is a well-established technique for uncertainty analysis. It means exactly what it sounds like. You roll the dice and keep rolling those dice, and eventually you work through the patterns of uncertainty. So within that framework, we can have a soil gas source that drives the model. We can have a groundwater source. After the model does its thing, the results are compared to screening levels. So those screening levels are entered as part of the input, and what we're going to see is what is the probability that these model runs exceed the screening level. And then a seemingly simple thing, but it helps facilitate correct use of the model, is the model choices are very flexible. So we're not going to force you to use metric system units. And then on top of all this, it generates an automated report that gives a brief summary, very concise summary of the model runs, and then it shows all the parameter choices that were used to generate that result. So you can see everything that went into cooking up the result. And so as I've been trying to emphasize, the primary focus of this is to add a line of evidence for site assessment and closure decisions, and we're doing it by making the uncertainty analysis practical. Sometimes I say that we can make more certain decisions by incorporating uncertainty in our decision making. Okay, so let's just take a look at the sources. This schematic represents a soil gas source. So there's a building, there's a distance from the bottom of the building to the sample, there's a depth of a sample, and there's this zone of soil gas contamination somewhere above the water table. Okay. So one of the things we'll see in PVIScreen is that it then takes what you've put in as input and it generates a schematic. And there's several distances. This is done because there's several distances that are needed to run the model, and it can get confusing. I would get confused when I was testing things, as to what depths I'd really put in. So you can see it visually. And in this case, we have the soil gas sample, which is above the water table, and it's at a depth of 3 feet below the land surface. The foundation in this case was half a foot below the land surface, and then there was something like 7 feet down to the water table. But we're really simulating transport from this sample at 3 feet and its potential to go into the building. Okay, we can also have a groundwater sample. Once again, we're concerned with the bottom of the building, distance to the sample, the depth of that sample, and then in this case, the sample will be at the level of the aquifer. Okay, so there's one complication with using groundwater to drive the model, which is the capillary fringe. Excuse me a second. Transport through the capillary fringe, if you look at the literature, is a complicated process. You're basically going from fully saturated conditions through partially saturated conditions, which can have complex transport associated with them. So this shows, however, a set of data that was published in 1993 And it was for a chlorinated solvent, so there's no aerobic biodegradation here. And what it shows is, on this side, the depth in the laboratory column versus the TCE concentration, or the relative TCE concentration in this case. So as you come up to the level of the water table, you begin to see a decrease in the concentration of this solvent. And as you go from the water table to the top of the capillary fringe, there was a drop of about 10% in concentration. Okay, so over here on this graph is again the depth, but the moisture content. So here's the water table, and as you move up, this is called the tension saturated zone, where there's still water, but it's held by suction. And then as you get above the tension saturated zone, you see a reduction in moisture content. Okay, and the key result that we've used in PVIScreen is right here, is this 10% reduction in concentration from groundwater on up to the top of the capillary fringe. Okay, you might justify that or feel that more reduction is warranted or not reducing it. So that factor can be adjusted in the model. But in the simulations, we're going to see that 10% factor is included. And in fact, this 10% factor was included in BioVapor also. I searched for data to support it. Okay, so then again, there's a schematic, and in this case, it shows the groundwater source with the source being right down at the water table. And again, the relationship with the building. Okay, so a little bit of the details of how it works. I said it's written in Java. The interface is written in something called Java FX, which means it merges right in with the Java as one single code. That's probably not too important to you, but what is important is that all the inputs and outputs are saved in text files. Okay, so there's a special file extension for PVIScreen. It's .pvi. And so typically the input file will have the name, problem name, .pvi. Okay, there'll be an output name that has the same problem name in it, and it'll have a date stamp and then some more extensions. Okay, the most important thing about the extensions are the last one, which is CSV, which stands for comma separated value. Okay, so that means you can edit the output in Excel. You can also edit the input files in Excel. I don't recommend that unless you get a lot of expertise with the model, because it is actually kind of particular, very particular about the way the input data is structured. But we can look at the input files in Excel. Normally, we're going to use the graphical interface to generate and edit the input files. And we're going to use the interface to display the results on this file. And we'll see this live during the demo part. Okay, so once it starts to run, the first thing you see is this blankish screen, and there's a series of buttons across the top. The ones that are active and that you can do something with are highlighted in green. And so when you start, all you see is select a file, about, and exit. So you're going to really want to focus on selecting the file, and then everything is going to run, that we do with the model, will run from left to right, even though I said right to left on the slide. Yeah, everything goes from left to right. Okay, so what about the approach to uncertainty? Well, We're going to allow most of our parameters to be treated as being uncertain, but we're going to incorporate known parameter values where we have them. So we're actually going to have a mix of known parameters with uncertain parameters. And so the interface allows constants. Those are our known parameters, things that we can estimate pretty well. And then we'll also allow for uncertain parameters, and we're going to characterize those by a range that goes from the minimum to the maximum. There's, and we'll see that, or that's actually indicated over here, where this one is said to be constant, and then this one is uniform between a min and a max. Okay. The model in the command line version also allows much more complicated empirical and parametric distributions. The parametric distributions being like a normal distribution. Those aren't included in the GUI, and that's not going to be included in today's presentation with one exception. But those are possible. By and large, data are limited, and so the number of times you're going to have an empirical distribution is pretty limited also. Okay, this is what the screen looks like once we've selected a file. So we have selected a file, and now some more options are available, and we're on the View and Edit option. You can view the schematic, or then you can prepare to run the model. This shows the Building and Foundation tab, where we can enter building parameters. And so the first ones are thought to be constant. You know, for example, ceiling height is a parameter. So we ought to be able to determine the ceiling height for a building. If we can't, we can treat it as uncertain, but that's one that you're more or less going to know, as is the dimensions of the building, the length and width of the building. When you get into some of the other parameters, maybe I don't know the foundation thickness too well. There's a parameter called the crack width down here. So this is something that comes from this original Johnson-Ettinger model that is actually included in BioVapor and hence PVIScreen also. There's assumed to be a crack in the foundation. And it's assumed to be a perimeter crack, and you're supposed to enter a value for the width of that crack. It's unlikely that you're going to be able to observe any crack, and it's unlikely that a crack slab is even characterized by one crack width. As an aside story, we renovated one of our buildings when I worked at the Athens, Georgia lab, and we pulled off, or the maintenance guy pulled off all the flooring, and so you could see this exposed slab that was 35 years old, and it had a very fascinating crack pattern. The corners were cracked off where the columns had come down. There were all sorts of cracks running across the foundation, and they varied in width. I mean, there were some you could stick your little finger in. So crack width is a very uncertain and unknown, perhaps unknowable parameter. Another one is the air exchange rate. It's unlikely at most lust sites that you're measuring the air exchange rate of either a convenience store or a residence. And this can be an important parameter. If the contaminants actually make it up to the foundation and don't biodegrade before they get there, if the house is drafty or not makes a big difference. So the air exchange rate can be important under certain circumstances, and it's likely not to be very well known. What you're seeing right here, this is a range that we put together of commercial air exchange rates. So obviously they could vary in a building, but we're basically using this range of 3 turnovers per hour per day to 10. Another notable set of parameters are the chemical parameters. And one of the things, one of the big advances in BioVapor was that it allowed and encouraged you to enter all the data that you have and to completely as possible, characterize the soil gas. And the reason you want to do that is that when you have the biodegradation being driven by the oxygen, you don't want to assign all that oxygen, just assume all that oxygen goes to benzene, because then you're going to overestimate biodegradation. So the amount that's going to the benzene is only a fraction of the total, because it's also going to these other constituents that also exert a demand for the oxygen. Okay, and so we want to put in as much data as we have. And in this example, and this is one of the ones from the state of Utah, we have BTEX first, we have naphthalene, we have MTBE, and then picking up the bulk of what we were able to put in is the TPH GRO. Okay, if we had more data, it would be better to put in more data. So that's always a guiding principle here. Okay, for each of these constituents that we have, we need to have a screening level. Okay, so what's entered here is the screening level for each constituent that we're simulating. And in this case, the screening levels came from Utah's site-specific spreadsheet. So these are calculated offline and entered here as data. So the choices are the state-specific screening levels, or in other cases, the EPA RSLs, the regional screening levels. And I've given you the link for the EPA RSLs. Okay, so let me jump back to one slide on biodegradation. This is the one example where we're using an empirical probability distribution. And the factors that control biodegradation are uncertain and possibly variable, in that the data that are available have been put together from various sources. And one of the things you can see on this figure, which is a plot of the attenuation factor, which we don't really need to think too much about what that is even, but you notice these lambdas, which are the degradation rates. These numbers vary by at least a factor of 100. Okay, and so this is something that we don't have the ability on a site-specific basis, for the most part, to go out and determine this for a site-specific value. So biodegradation in this variability has an impact on the results that we're going to see, but how do we know what that impact is? And the reason, what we're going to do here is to go through and treat this as a variable parameter. It will always be treated as a variable parameter, and in fact, you won't see it on the input screen. The last group of parameters I'll talk about are suggested values, and these are more values that it's unlikely you would determine on a site-specific basis. But if you have the ability to do this, you can change these values. What's highlighted here are things related to airflow and oxygen. There's a couple other categories that we'll look at when we do the live demo, but these sit there on their own. As I said, you can change them, but it's unlikely you're going to have a way to get good estimates of these. Okay, so once we have all this data, what does the model do with it? So PVIScreen takes and grabs all the parameters that are constants, all that have the uniform distributions, and then in the case what we're going to see today, it's going to pull in this data-driven biodegradation rate distribution, and it pulls those into the model, and it does multiple runs. This is the Monte Carloing of it. The Monte Carlo processor is set up so that it grabs all parts of every distribution so they all get folded in their complete ranges. And then it runs it 1,000 times. That's one thing we can change. We can make it run more, but we use 1,000. And then it takes and post-processes those 1,000 results and generates a frequency distribution. It could also be called a probability distribution of the concentrations in indoor air. Okay, so I've drawn this kind of odd-looking schematic that represents the fact that there is a distribution of indoor air concentrations that are generated by the model. And this is part of the output that you'll see. To interpret this, you could pick a concentration, and if I pick this concentration here at the bottom, the probability of any result giving me a concentration of that or above that level is down at 0. As I move up the curve, the probability of this concentration would be right off this curve. So a concentration of anything up to this level is written off as this probability. And then the top, I get this concentration, it's at the 1.0, so it means everything is below this value. There's nothing higher than the one that's at 100. And that's going to be something we're going to look for. What is the concentration that every simulation came out below? Okay, so I'm going to show a couple snippets from examples. This is a site in Utah, and the simulation was driven by soil gas. So for this situation, there was a leak at a convenience store. The contours represent benzene and groundwater. And you'll see they go over here to this off-site restaurant. So one of the questions was, is there potential for vapor intrusion in this off-site restaurant? The red circles indicate soil samples that exceeded Utah's soil screening levels. But here we're going to focus on vapor intrusion potential from contaminated groundwater. This is in the user's guide. I'm not really going to go through all the details of this. I'm just kind of setting this up to say that this is a case that's driven by data from a soil sample that's 3 feet below the land surface, and we have concentrations that are hard to read of benzene, TPH, and so the model is driven, and others, and the model is then driven by this soil gas data 3 feet below the surface. And so we're going to say, well, are there impacts to the off-site restaurant or not? So once again, it generates the schematic, actually the same one you've seen before. And then this shows the results. And so the main result here is indicated in 2 ways, one on the graph and then one on the table. And the table is the most direct representation of the results. And what it reads is it says that 0% exceed the screening level of 0.5. This particular one did not have the unit, but it now draws the unit. So none of these for benzene exceeded the screening level. That's also indicated on the graph because here's that point of probability of 100%, and every calculated concentration is below that. So every calculated concentration was below the screening level, and it was pretty far below it. This example, which is also in the user's guide, is an example that shows when there's an impact indicated by the model results. This shows, again, a leak at a convenience store. The red lines are benzene concentration contours, and this line, this innermost contour is 5 milligrams per liter in groundwater. So this site is significantly hotter than the other one. And then there's free product levels indicated in these darker yellow boxes. So there's product around here. So we expect this is a hotter source. This shows, again, the vertical slice. And we drive this simulation with data from this monitor well 3 from groundwater data here. And it was taken from a time when there was not product in the well. Okay, so when we run it again, for this situation, again, the main result is indicated here. And what we're seeing is about 69% of the runs exceeded the screening level for benzene. Okay, so the model is indicating here there's a significant potential for vapor intrusion from this line of evidence. You see it also on the graph in that here's the screening level marked with an L, and then there's many results that are higher than the L. The results with higher concentration and our point where there's 100% of the run. This one also shows a V, which is if you average all the parameters together, you would get this concentration. So if I just ran the model with all the parameters as average, that's where I would be. And then given the probability distributions, the M is the most probable result. So the most probable result is above this screening level also. Okay, I said at the beginning, all the results, all the data are then compiled into a simple report. I'll show it live in a few minutes. And then all the results are available in the CVS file that contains the output. And you can look through that. All the 1,000 runs will be individually indicated in this file, their results, the parameters that were used, and then as you scroll down through this file, you then see the output histograms that have been created by the post-processor. Okay, so what are the secrets of PVIScreen? These have never been revealed before. Well, this is written in Java, and so Java has to be enabled on your computer. We've run into cases where it's been disabled because of security reasons. So you might have to ask some admin people to make this available to run. PVIScreen has to always start with an existing file. And you're provided with 2 sets of existing files when you download the code. They're both examples, and these largely come from the user's guide, and then there's templates. Since the templates are so important, they're regenerated every time you run the model. So you can delete them, or they could get corrupted. They will always be rewritten, and they will always be there every time you run the model to grab the template and start filling it in with data. Okay, it's a good idea to create some project directories, one for each project. And one of the reasons this is a good idea is that all the files, the result files, are saved with a date and timestamp. Okay, and so if you run a lot of cases, you're going to generate a lot of files that are all unique because they're timed and dated. But that also means you can go back and see exactly what you've done. But these will pile up over time. Okay, sometimes something doesn't work exactly right, and you may not see the results displayed. If this happens, you can exit and restart, and most of the time it takes care of that problem. That's an issue I'm still tracking down why that happens. Okay, as I've kind of implied and emphasized, concentrations and data are needed to drive the model. So this is pretty much unlike the situation that the Denver Post reported on. We don't have a hypothetical concentration we're starting with. We need to be starting with something that comes from our site assessment work. Then, as I said, biodegradation is always treated as being uncertain. And that's because we just don't have a way of estimating that at a typical loss site. Okay, so a lot of the times when you run a case from contaminated groundwater, what you're going to find is that it shows no impact. And that's the biodegradation working in favor of preventing PVI. But when an impact is shown, and if you run the model more than once, what you'll find is the model doesn't give you the same percentage every time. So one time you might get 69%, one time you might get 68%. And that's because you're running this randomly 1,000 times. Well, the key word is random. So there's some randomness. If it bothers you that there's this 1% variation, you can increase the number of runs. And I've actually not done this in a long time. For a while I was running it 5,000 times or 10,000 times. That's a little bit of overkill, but it would take away this variation. And then the second point is if the result shows very marginal exceedances, and here I said less than 10%, but it might be much less than 10%. So if it's like 0.1% of the cases show an exceedance, you should consider going back and refining the ranges of your parameters. And I mentioned one thing, which was the air exchange rate. So if you know that the house is drafty, you might want to revise the range for air exchange rate. Or some other parameter, like you might want to look at moisture content. And that I would recommend doing in cases that just show a very small range of impacts. And then maybe that's the result, and then a decision has to be made of, do we think this is indicating a need for further investigation, or can we go ahead and make a decision about the site? So once again, I'm showing the flow chart from the PVI guidance framework. And so I want to emphasize that PVIScreen is one line of evidence that could very well be brought in during this time when we're looking at the vertical separation distance. And especially if we have a marginal case where we either don't have a good way of getting the separation distance, or perhaps it's borderline. That's an ideal place to start looking at using the model. Okay, then in summary, I kind of just made some of those points, but I'll just repeat that immediate threats are handled first. You wouldn't even consider thinking about using this model when somebody is complaining of smelling vapors. The site characterization and development of the conceptual model has to come before we start using PVIScreen, and we might choose to integrate use of the model with the site assessment process. And of course, all afternoon we've been talking about the parameter uncertainty and its ability to add a line of evidence to the assessment. Okay, so we're going to move now into the demo part. So Hal, can you see my screen at this point?
Yeah, Jim, I see your SharePod number 9. It's waiting, I think, for you to click on it and share your screen.
Okay.
There you go. And for those of you participating, you may want to enlarge this next section to take up your whole screen. There's a icon near the top of the blue bar that has 4 arrows going different directions. That's how you enlarge that window.
All right, so I just went to the EPA website to the PVIScreen page. Hal, can you see that page?
Yes.
Okay. And let me ask how we're doing on time.
You've been at it about a little over 50 minutes total.
Okay. All right, so this is the web page where you can download PVIScreen from. The first link as I scroll down here is for the user's guide or the documentation. And I'm going to go to the download of the model. We have a pretty fast connection, so it's not going to take long. It's about 7 megabytes. Okay, so here it is at the bottom. Okay, so this went into my downloads file folder. That's not where I want to work with it from. I'm going to go over to another place on the C drive under my documents. I'm going to create a directory for this, and I'm going to call it PVIScreen Webinar. Then I will go back and grab the download. And paste it there. Okay, so I've created a directory for PVIScreen, and what the download consists of is a zip file. And I will now go on and unzip the file and unzip to here. Okay, and when it unzips, this is what you should see. A file called projects, or a directory called projects, a directory called SRC, the jar file, that's the executable, and this zip file that we just got it all out of. We can go ahead and delete this just to get it out of the way. So the projects have the example files. These are from the user's guide, and the templates that I mentioned. And just for fun, I'll delete these right now, because what you're going to see is when I go and run PVIScreen, it's going to recreate those. So I'm trying to emphasize that you really don't want to store your own results or data in those files. Before I start, I'll mention SRC stands for the source code. And in the source code directory, you have all the source code for the model. So these are all the Java files, and then there's a separate file for the user interface. But of potential importance is there's a file called system data, and system data contains the files that hold the chemical parameter information. And so if there's a need to change chemical properties, it's done by these files. Okay, but before we talk any more about that, let me go ahead and run it. This is called a jar file. It's an executable file. It's a Java file, and it is pops up pretty quickly. You get everything out of the way. Okay, so this is what you see when the model first executes. We saw earlier we only have a couple of the options available. Selecting file is the one that's going to be most useful. And it automatically points me to this directory called projects. And I have the choice of examples and templates. And you'll notice that the templates are back, even though I deleted them. Okay, so I'm going to start with this template. And let me say I'll start with the sample groundwater input from a commercial source. Okay, and after a couple seconds, the input pops up. So we're on the view and editing of the input. And so, of course, we start with the basic information. This is the webinar site. We're in the cloud somewhere. That'll be me. So I go over, the first thing we see is the building and foundation. We talked about parameters here. Vadose zone, I did go through these, but this is where you put in your depths, depth of the sample, depth of water. Since this is a groundwater case, the depth to sample is the same as the depth to water. So moisture content, porosity range, organic carbon range, soil temperature range, and then the chemicals. So this was characterized by BTEX, naphthalene, MTBE, TPH-GRO. Let's say I had TPH-DRO also, and add it, and then it gives me the chance to add that concentration. I look at screening levels. Here's the screening levels that came from the Utah case example. And since I added a chemical, I just added a slot for a screening level for DRO. Okay, so before I run it, I'm going to take that away. So I get into my suggested values. These are the ones you saw in the PowerPoint. This concentration adjustment, this is this factor that accounts for transport across the capillary fringe. And then model control, these are the ones that for the most part you really wouldn't touch except if you wanted to increase the number of simulations. Okay, so let me just go through this process. Okay, so there I can look at the schematic. This is like what we've seen before. I push this prepare to run button. Okay, since I changed something, or it thinks I changed something, it's going to want me to save it under a different name. I did, and now I'm going to run the code. Let me template. Change the name and put a 3 in it. looks like it's done. So that gives you an idea of how long it takes. So it didn't take very long. Depends on the speed of the computer and the speed of disk access, because there's a lot of reading and writing to the files. And we can look, as before in this example, this is not indicating, so all the runs that were made, none of them indicated an impact from benzene above the screening level. You can see that on the chart because the screening level is indicated here, and then these are the individual runs, and the calculated concentrations are so low, they're below what's measurable, so they're not displayed, and they would go way off to the left. So there was this comment a minute ago on the chat of, well, you have a vast range because of the ranges of these parameters, and actually you do. So incorporating this uncertainty does generate a vast range of outcomes, but in this case and other cases that you're going to see, they indicate there isn't a potential for vapor intrusion. Even if it does, a lot of the range of the outputs from the model are concentrations below anything you could measure, so they're completely irrelevant. So if those concentrations are that low, they don't add anything to a weight of evidence for or against vapor intrusion, so they are irrelevant. But in this case, what we see is that for benzene, the 1,000 runs didn't indicate the potential. You can look at toluene. The model turns off the graph if those concentrations are too low. Here's 0% exceeded the screening level. Ethylbenzene was also 0. Xylenes is 0. Naphthalenes is 0. MTBE was 0. TPHGRO is also 0. So for every one of these constituents, the 1,000 runs of the model indicated no potential for vapor intrusion. Okay. All this information is consolidated on a report. Okay. Right now, the default is that it will pop up Internet Explorer. I've worked on an option to choose the browser of your choice, but that's disabled at the moment. Okay, so this report goes through a little bit about the model, tells about the files that were used, what the file names are, description of the site, how you define the source, how you define the screening levels, and then the result is right in here. It says percent simulations above the screening level, and every one of these is 0. Then it goes through to give a recitation of the input data. So you can look and see, well, what was done to get this result. And so first are printed all the variable parameters, followed by the constant parameters. And you'll notice one parameter, the foundation thickness, it says it's effectively constant. That means we actually entered it as a range, but put the same number in for both. We can go back and look at that. And then the chemical parameters are then listed. These properties are the chemicals that were used. So that's the report. Okay, the report button is a little bit touchy. So if the report doesn't appear, you can look in your project directory, and I changed the name to be commercial-3, and so I'm looking for the commercial-3 HTML file. And I don't know why I don't see it. That's a mystery right now. It didn't go anywhere else. It's got to be around here somewhere. Okay, well, that's a little bit of a mystery to me. What I was trying to say was you can go look for the HTML file and then just double-click it, and it'll come up in your browser if it doesn't come up in the right report window. So I'm going to go out, and I'm going to start again. Not that there was a particular need to at the moment. Put it in Documents. Let me select one of the example files. This is a groundwater example from MW3, which is the one that shows the potential for an impact. That schematic, let me run it just to get the results up here. Quick enough, it might not be. You can watch the file filling up. So it generates about a 6 megabyte file, which contains the 1,000 runs and then the post-process statistics. Okay, so this one, in contrast, shows the potential for impact, and it does show many orders of magnitude variation in calculated concentration. And so this had to be displayed on a log scale. But the main result here is that in this case, 43.7 of the 1,000 runs exceeded the screening level for benzene. 0 for toluene. Okay, so this level, once it gets to 1.0 in probability, every simulation gave a lower concentration than this one, and below the screening level. And so there I have 0 exceeding the screening level. Ethylbenzene, same thing, everything below the screening level. Xylenes, they are below. There must be a glitch that didn't print that. Naphthalene, everything below the screening level. MTBE below the screening level. TPH-GRO, about 43% above the screening level. DRO, 6% above the screening level. Get the report. Same kind of thing we saw before. So here you see the concentrations that were in. These are in the milligram per liter range for BTEX, so we know this is hot. And then down here, it ranks them in order of the fraction of simulations above the screening level. Benzene being about the same as TPH-GRO, about 43%. Once again, the variable parameters followed by the constant parameters followed by the chemical input and properties. I'm just going to go back and run this again. There you can see it's running again. Now, I didn't change the file name or anything. But this generates a unique set of files because the date stamping. So these have a different date stamp. I'm going and picking it again. It didn't display the results like I needed it to. Okay, so if you remember before, this number was 43 something. This time it's 44 something. So they do vary a little bit, and they'll vary about 1% like that. And that's because of the random nature of picking it 1,000 times. So Hal, how are we doing on time?
You've got about 12 minutes or so.
All right, why don't I break off from this and we can have some questions and answers.
That sounds good. I've actually been monitoring the chat as you have. There were really kind of two questions. One was, does PVIScreen contain data for EDB and 1.2 DCA?
I know, yeah, let's look. Let's just look. That's the simplest way to answer the question.
Okay.
I'm sure they do, but I'll show you where it is. It's going to be in the input data files, or the system data files, sorry. And I stuck this over here in documents. So if I go to the source directory, system data, and I'll hit this chemical properties file. And so that's going to call up Excel. And so this is exactly the data that, excuse me, are used. And EDB is here. So I don't have DCA at the moment, but I can add that.
Okay. Another question, Stephen Bauman had typed quite a few, I don't know, comments, I guess, about Monte Carlo and the uncertainty in the data and how that was addressed in the in PVIScreen. I don't know the specific question, so Stephen, if you're listening still, unmute yourself, #6, and ask a specific question. Now would be a good time. And if anybody else has a question, unmute your line. It's #6, and go ahead and ask Jim a question.
Okay, with that as an opening, I'm going to go back and show something about the chemicals that I forgot on the first time through. So I'm just going to pick up one of the templates, open it. Okay, so on this Add Remove chemical button, it gives me a list of chemicals, and these are the ones that it has data for. So these are the things that we can currently simulate. And so I included the TPH criteria working group or aromatic and aliphatic fractions, if someone's using that. And then we also have TPH GRO and DRO. And those are included to further the end of being able to include as many constituents as possible. And of course, we're always open to including more constituents like the request for 1.2 DCA.
So any other questions for Jim? Anyone? Well, hearing none, I'll give people another 30 seconds, and then we'll end the webinar here. Is that okay with you, Jim?
Yeah, that's fine.
Unless you
can you hear me? This is Chris Prokop.
Yeah, hi, Chris.
Just one quick thing, and I don't know whether Jim, you mentioned this already, but I know I mean, obviously your schedule's pretty loaded, but in terms of, you know, let's say I chose to run it for a site where I'm anticipating data in the next couple of months, and I mean, obviously I don't want to take too much of your time, but if I had specific questions, would you be available to sort of troubleshoot?
Yeah, certainly.
Okay.
And usually the best way to do that is if you generate an input file and maybe it doesn't seem to work right, to send me that input file and I can look through it.
Okay, great. Great, sounds good.
Yeah, in fact, my email is listed on the EPA website as the contact person, so if people do run it, have issues, just contact me. In all honesty, last demo, it didn't display the second time I ran that example, and I've got to track down that bug. And so what we'll be doing is when there are more bug fixes, we'll be uploading corrected versions of the interface.
And then this is my last one. So I know that when you brought us to the main website, there was the kind of the user's guide, I guess, and then there was the actual model itself. So does the user's guide essentially, you know, give the I don't know, the Geology 101 breakdown of the thing to the reader? Kind of the basic.
Yeah, it pretty much, the presentation follows roughly what's in the user's guide, and of course the user's guide has more details and more on the individual parameters. So it's obviously good to look through the user's guide, especially with regard to looking at the parameter values for input.
Okay, great, thanks. Actually, Hal, I do want to ask you a question later on. I mean, I can do it now or later, but you know, can I call you at your office after this is over?
Yeah, that'd be fine.
Okay.
Okay. Does anybody else have any other comments or questions they'd like to make before we wrap up? Going once, twice. All right, well, I'd like to thank Jim Weaver for putting on this presentation today. I know he put a lot of time into it and spent a lot more time into getting the code up and running. So I hope that the participants, that you all got something out of this as well. And we look forward to hearing, you can share some of your experiences using PVIScreen. That would be very helpful for us. So having said that, I guess we are adjourned. Thanks again, Jim.
Yeah,
All right, you're welcome. Bye.
Bye-bye.
The leader has disconnected. The conference will be terminated in 5 minutes.